Hey friends, it's Ben again. This is a quick video about the idea of limits. As you can see, it's being made from my back porch in the evening, so a little crisp. But, so your basic notion of limits that you got in Calc 1 is going to serve you pretty well for what we talk about as limits in Calc 3. Most of the time when you want to calculate a limit, you plug your numbers in. If you don't get 0/0, you're done, you know. Other times you have a little bit more to do because of the algebra, that sort of thing came up a lot in the Calc 1. There is no L'Hopital's rule, okay? Unless you do something to make your limit be about just one dimension, and then you have it down as just one variable and you can talk about L'Hopital's rule. But without that, we don't really have the exact equivalent, okay? But in any case, let me give you the technical definition here from my iPad. I wrote this stuff out ahead of time so that I wouldn't get it goofed up. So, can I just turn that on side? Yeah. All right. Probably is a little bit easier to read. So here's our definition for what a limit is, okay? If you have the limit as xy goes to ab, usually we're talking about it going to 0/0 because that's just the easiest case to talk about. But you find if you have the limit as xy goes to ab of xy equaling L, that means that if you've got any positive number epsilon, that you can choose a positive number delta so that whenever this square root down here, now I'm just going to do that in yellow. Whenever that square root there, that distance, is less than the delta, we find that the absolute value there, the difference between your function value and your limit, is less than the epsilon you wanted. Okay, so you might ask, what? What the heck were you talking about there, Ben? That was just crazy symbol stuff. Well, that square root of x minus a squared plus y minus b squared ought to seem kind of familiar to you. That's the distance formula. So when we say that that square root is less than delta, what we mean intuitively is just x, y, and ab, those 2 points, are close. And when we say the absolute value of f of xy minus L, we just have two numbers and we're looking at the distance between them. So if the distance from xy to AB is small, then the distance from f of xy to L is small. That's really all limits are saying, both in Calc 1 and Calc 3. So then your question is doubtless, what do I do? How do I use this? First thing is always plug in the numbers you were given. If it's 0/0, you got to do something. If it's infinity over infinity, you got to do something. But if it's not, you're just done. Okay. So if you do get 0/0, look and see if you can factor things. If you can factor things out and cancel, boom, that often does it for you. If either you can't factor it or the factoring doesn't help, take a look at a graph. See if that tells you a little bit of something. Then this last bit here is the part where a Calc 3 limit is different than a Calc 1 limit. When we talked about limits in Calc 1, we might have a function that did something like this, and the idea was that you could look at your limit from the left and your limit from the right and see that you got different values for those. But here, instead of having a line and coming into this point on either side, like you could do in one dimension, now we live in a plane and there are an infinite number of different directions that we could try to come into that point from. So looking at graphs often gives us an idea of what's going on. If on the graph you can see two different ways to approach the same point, and it looks like your graph doesn't agree from those two directions, then that shows you how to tell, how to set up your answer so that you can explain that that the limit doesn't agree. So, what's the trick? Sounds like I'm saying most of what we're going to do is look at graphs. The trick is that most of our limit stuff really isn't going to require quite such tricky stuff as what we do here. But we need to realize that there are some exceptional cases, and we need to try to see if we can do the algebra in order to prepare for them, right? So we're going to look, first of all, about a limit that should seem a little bit familiar. The limit as xy goes to 0, 0 of sine of x squared plus y squared over x squared plus y squared. If you remember back in Calc 1, you did the limit as x goes to 0 of sine x over x. So this is pretty similar, and I've got some graphs going on. Come on, there we go. All right, so here is my graph here, and as I zoom in, you can kind of see what's going on. I'll kind of turn it over so that you can look. The gray plane that's showing there is the plane z equals 0. And so in close to the origin there, you've got something that's kind of got the top of a hump there. And it looks like the limit that you're getting is 1. So when we talk about this limit here, we're actually going to go ahead and say that the limit is 1. If you're asked to back this up, then you'll let r be the square root of x squared plus y squared. This is something that's we talk about often as polar coordinates. Then what you would be talking about on this then is taking the limit as r goes to 0 of the sine of r squared over r squared. And that would turn out to be 1 by the limit that you did in Calc 1, all right? So looking at that graph gave us the kind of insight that we needed there. Now, this one is a little bit more painful, okay? When you plug in the 0, 0 to it, just like with the one for the sine, you've got 0 divided by 0, but this 0 over 0 is going to behave a little bit differently. And so I'm going to come over here to my graph, and where did I put that one? There it is. All right, so as soon as you see that, you can spot that whatever the heck is going on, it is rocketing off to infinity around close there. So let's go back to what we're writing out and see if we can do something to simplify it a little bit. And if you remember all of your algebra, you might spot that that bottom can be factored into x minus y times x squared plus xy plus y squared. It's a difference of cubes. All right? And then when you cancel those out like that, the limit you're taking is going to be just 1 over something like that, right? And from taking a look at the graph, you can see that that's going up to positive infinity, no matter which direction that you're coming into the origin 0, 0 at. You are ending up having it from every direction going up towards infinity. So there's a limit that you might see something similar to, right? Right, here's one that, again, you'll see something similar to on your homework, but it's not exactly the same, all right? First of all, if you cancel those two x squares, I'm going to come shake my finger at you, because, you know, you can't do that. It's got to be a factor of the whole top or the whole bottom before you can actually cancel it out. But the thing you really need to spot here is that all the powers on this seem to be the same. On the top, you get an x squared. On the bottom, you get an x squared plus y squared. I think you've got an example in your homework that has like an x times y over x squared plus y squared. So this is going to behave just a little bit similarly to that. So let's look at my 3D grapher here. And I prepped all these ahead of time because they're a little bit of a pain to have to type in. So, all right. So here's what we've got going on here. And watching it as it turns around there is kind of giving us a little bit of an insight. This has this kind of a weird setup that it looks like it's got a pinch in the middle of it. If you look there along the, I can't tell. I think this is the x-axis here. That's the red one. But it looks like along that on the top, you're getting stuff looking like it's at the level of z equals 1. But then along the y-axis, the green one, it looks like you're getting stuff happening along z equals 0. So that suggests that coming into the 0, 0 from two different directions is going to get you two different answers. And that is going to say that this does not exist. And no, you don't get to just say that because you looked at a graph, okay? You have to back it up. And so you'll have to say along x equals 0, right? This will become the limit. Now remember, x is going to 0, so that means the top is just 0. And on the bottom, you've got 0 plus y squared. But y wasn't set to 0, it's just going to 0. So we get the limit, so y goes to 0 of 0 over y squared. Now remember, the top isn't going to 0, it already is 0. So this limit will turn out to be 0. But along y equals 0, you would have the limit as x goes to 0. The top is still x squared. The bottom is x squared plus 0. That's the limit as x goes to 0 of, well, those just cancel and you have 1. And this limit does not exist because along two approaches to 0, 0, the limits disagree. Now the key on that, once again, is that we were able to spot that the limits were going to disagree by taking a look at the graph. Just looking at the graph doesn't tell you what to write down for an answer, though, it tells you, well, let me rephrase. It doesn't answer it for you. It tells you what you're going to have to look at. So you establish that that limit doesn't exist by looking at just two approaches where you got different answers, right? So if y'all take a look here, this is one that you're going to be doing on the homework, and it has pretty much that same shape to it. But now, where are those two approaches? Well, if the red axis is the x-axis, the green axis is the y-axis, that kind of a shiny area in there. Sorry, I can't point with a mouse or anything here. Wait, maybe I can. I hope you can see that. So I move the mouse across. Looks like it might be the line y equals x that's at the top of that peak. And so if you go down here and look underneath, looks like that might be the line y equals minus x. That might get your two approaches for you right there. You have to try it out and make sure, all right? But let's take a look at one that's weird, okay? So this one here, if you try out every straight line that there is, so I'm going to just go ahead and say along y equals mx. Technically, that doesn't quite get every straight line that there is, because if you get something with undefined slope, you know, but if you went along y equals mx and substituted here, now your limit is going to have x in it going to 0, but we're going to replace the value of y with mx. So we'll have x squared mx over x to the 4th plus, let's see, y squared, so m squared x squared. So that's the limit as x goes to 0. The top will have an mx cubed. The bottom, you can see, has an x squared that will factor out, and you'll be left with an x squared plus m squared. My m is a little hard to read there. And so we can cancel out two of those factors there. The top is going to, the top has limit as x goes to 0, and it should have this mx and x squared plus m squared there. So it looks like the answer we ought to get out of this is 0, no matter what straight line that we go on, right? But let's take a look at a graph for it. And which one was that? That was this one. Okay. So take a look at the weird thing that this does. If you look right there, can you see that kind of a cup shape that it's got? And if we turn it up here, we can kind of see along y equals, stop that, along y equals x squared, it's at the top of a peak. And we can kind of see on the graph that it's going to go in toward in towards z being 0.5. So if we go back here and say along y equals x squared and substitute that in, we get the limit, x is still going to 0. Now we're going to replace y with x squared. I'll have x squared times x squared over x to the 4th plus, let's see, y squared, so that's x squared squared, so that's x to the 4th. And that's the limit as x goes to 0, x to the fourth over 2x to the fourth. The x to the fourths cancel, and you end up getting a 1/2. So this limit, again, is an example that does not exist because limits along two approaches to 0, 0 disagree. Okay, and that's a lot of the tricky stuff that you have to do with these limits, is when you have to hunt down some particular approach that disagrees. But if you have a handle on this 3D graphing software, you can see a picture of it and zoom in and kind of figure it out by looking at it. Okay, so these have the weird advantage that there just aren't that many different examples. If you work through each of the examples that are in the homework, I really can't surprise you with anything when it comes test time. It's all the examples kind of work like that. And it's almost always a question of show the limit doesn't exist by picking the right two approaches. Okay. All right. I'm going to let you all do some experimenting with that and ask me questions, and you'll do all right with it. Thanks.